A very good morning to everyone. I, Nagma Anjum, Assistant Professor of EC Department, wholeheartedly welcome you to the session 8 of FDP on Machine Learning Application on Image Processing. It gives me an immense pleasure to welcome our speaker, Mr. Prakash G. from EL Technology, Bangalore. Welcome you, sir.
Thank you, ma'am. Thank you very much.
I take this opportunity to introduce Mr. Prakash G. He is currently working as a lead application engineer. He has about 13 plus years of experience in Core EL Technologies Private Limited, Bangalore. He has a technical resource person in Core EL University program team, providing the awareness on ASIC design and FPGA design flow concepts in academics with focus on Mentor graphics and Xilinx tools hardware. And he has a technical support specialist in Core EL Technologies, providing the customers from choosing the right FPGA for that and helping them to choose appropriate IPs for their design phases, and finally helps them to debug the board level problems and bring up the customer board. Now I would like to hand over the session to Prakash sir. Welcome you sir once again.
Thank you, ma'am. Thank you very much. I hope my voice is clear to all of you, and we are able to hear my voice.
Yes, sir. Yes, we are able
That's
to.
fine. I just wanted to just take a confirmation from you. That's it. Okay. Right. So good morning to one and all present in this meeting for the FDP, whatever you mentioned. Okay. Can you right? I hope everybody is safe and healthy. Yes. Right. So let's make this session of more interactive kind of thing. I prefer that way only. Okay. So if you have any questions, you can put me in the chat box. Is chat box is visible to me, ma'am? I can access it, right? Excuse me. Okay, right. I think not able to clearly confirm from you guys. Okay. Hello, can you hear my voice or not clearly?
Yes, sir. Yes, sir. We can hear.
Ma'am, I need some confirmation from you guys. Okay, why? Because what happens? No, I'll keep on starting. Okay, right.
Yeah.
So if something goes on wrong, you have to stop me in the middle or somewhere else, right?
Yes, yes.
That's the
Of
reason I'm
course.
asking all the questions to you, right? Nothing
Yeah, of
else, right?
course.
So I welcome all of you to this wonderful meeting. Okay, I hope everybody is safe and healthy also, right? Because
Yes.
you know the
Thank you.
situation very well. That's the reason I asked you the question, right? So let us make this interactive session as more of interactive kind of thing. I prefer, would like to have it. Okay, right? So let me introduce myself. My name is Prakash G. Okay. I've been working with Coral Technologies India Private Limited. It's Coral, Coreel. It's a core electronics, two words combined together. Coral Technologies India Private Limited. Okay, right. And I'm working as a right now as a senior faculty, as we are authorized partner for Xilinx training in India. Okay, I'm one of the senior faculty. I'm one of the trained faculty for a lot of corporate trainings as well as I'm handling a lot of defense trainings also. Okay, and I've been working with Coral University program for almost 13 years now, so more than a decade. Okay, and I've been supporting with a lot of educational institutes like IITs, NITs, and other stuffs. Okay, even I was part of the SMDP 1, 2, 3 programs also, right? So it's a special manpower development program, right? Even I've been associated with a lot of microprocessor-based challenges, which we have developed with IIT Madras recently, okay, and CIDAC Bangalore, okay, right? Excuse me, 1 second. Yeah, hello.
Yes, sir.
Okay,
Yes, sir, it is audible.
it's audible, right? Okay. Right. So I'm associated with Coral University program also, and I've been part of SMDP programs, microprocessor challenges, which we recently launched it with IIT Madras and other stuffs, right? So let us start our today's sessions. Like I got information that you are having some doubts regarding in Rakshit's sessions. Rakshit, who is my colleague actually, right? So you want me to ask now only, or you want me to ask a little bit later? Because my area is totally into like how I can use the Pink like Zinc SOC or Zinc Ultrascale plus SOC for machine learning based using a Python based application. How is it?
Yes, sir, you can ask.
Yeah, no, I got to know that somebody has got some questions regarding FPGA based implementation. Can we have that questions now only? Better option, I feel. Yeah, Indudi has raised an hand actually.
Sir, actually, my question is about HDL implementation, sir.
Come again?
That means how can we integrate with the pin configuration of FPGA device?
Okay, so pin configuration, to do that, we have to get the HDL code, okay? And in the Vivado, when you synthesize the design, right, we have an option to view those synthesized design, okay? And
Okay.
in that, we have IO pin planning tab will be coming. And from there, you have to enter the pin numbers for the appropriate design ports, whatever you have taken. For example, if you have taken reset is there, that has to be given with some input ports, like that way, we have to give the pin number. And we should know which pin is for what from the board devices.
Okay,
That's it.
depends on the device, we can send the
Depend
disk
on the board.
pin. Oh, depends on
Depend
the
on
board.
depend on the board. Because for example, if I'm using Z pink Z2 board, which I'm having it, right? So that pin number will be P14 for something switch for switches, but in some other device it will be C17 that way.
Okay, sir. Okay, sir. In that HDL coder only, we have to assign the pin configuration, right?
I don't know about HDL coder. Let me be clear to you. I'm from the FPGA background, so I'm from totally from the Vivado.
Okay, sir.
See, HDL coder will give you just the RTL code. Whether it
Okay.
is synthesizable or not synthesizable, you have to check it out.
Okay. Okay, sir. Thank you, sir.
Right, right. Okay. Any other questions? Any other has raised their hands, ma'am? Okay, then we'll have those questions and answers a little bit later only. Okay, right. So today, as per our agenda is there, right? So it is we are doing. Excuse me. 1 second. Okay, right. So we are doing the Pink Python productivity on Zinc. Okay, right. So even you can use Zinc also, or you can use even Zinc. You can use even the Zinc MPSOC also. Okay, what is this Zinc MPSOC? Any idea about those things? Anybody has having some ideas? Any idea? Any idea about that? Right. So most of you might be aware, like Xilinx has got different families, right? Yes or no? Right? So what are those different families are there, right? So right now we would like to bring to your high notice that almost most of the companies, like in companies like private customers also, even with public customer defense and DRDO labs also, right? So they are using, most of them, they're using 7 series and above devices. So you should always keep it in mind that you have to go with the 7 series and above devices. Okay. So what are these 7 series? You might ask the questions for us, right? Okay. So let us start with our today's session. Okay. I am sharing my screen. Let me know. Okay. Are you able to see my screen?
Yes.
Okay. Okay. This is the first slide. I am moving. Is my first slide visible? Welcome, Xilinx University Program, Coral Technologies.
Yes, sir.
Okay. I am changing it to the second slide. Outline.
Yes, sir.
Okay. So there is no delay there, right? So it's going on smoothly,
Mm. Yes, sir.
right? So just want to confirm you from your end. That's it. Okay.
Yes, sir.
Right.
Yes.
Right. So let us start our today's session with the FPGA families and little bit of architecture. I'll not go in depth of the architecture because I know that time is a little bit less here. Okay. Right. So we'll be seeing about the pink framework. What is that? Okay. And we'll be seeing about the Jupyter notebook interface, how we can, we are having it with the help of the board, whatever we're having it. Okay. Right. And we have some small demo on machine learning based applications also available on the pink sector board. Is it clear? Any doubts to me in this? I'll not be able to access the chat box now because I have shared my entire screen. That's the reason, right? If some question comes, please, I want one of the faculty member who is taking care can just stop me at the point. Is it fine? Yes?
Okay, sir.
Okay. Thank you very much, ma'am. Right. So, I was telling you about the 7 series and other stuffs, right? So in Xilinx, right? So we are one of the Coral Technologies, the Coral University program. So we are distributing Xilinx products, Xilinx software, Vivado software, Vitis software right now. Okay, right? And even in Karnataka and Kerala, we are even associated with MathWorks, MATLAB tool products also. Okay, and even Mental Graphics products and Stevens products also we are associated with, right? So you can contact us for any of the requirements for you on VLSI design, embedded system design, machine learning based applications, IoT based applications, so SoC designs, system on chip designs, right? So C to RTL coding, or even if you want to have some sort of requirement on PCB based designs, right? So you can contact us, right? So we have different product category available for you for any of the particular applications what you are looking out for that, right? So that is one thing I would like to bring to your notice. Okay, right? So in Xilinx, as your authorized partner for the Xilinx in India, right? So for the university program, we are one of the premier partner for Xilinx in India, right? So Xilinx has got different families, right? So in previously we had Spartan 2, Spartan 3. You might have heard about these things, right? So but nowadays ISC is almost closed, for completely closed, not almost, completely closed. Okay, and right now they are using completely the Vivado. Okay, right? So this Vivado is a tool which we are using it for synthesizing, implementation, right? Bitstream generation. That is all required for us to do an FPGA based implementation for us. Okay, right? So you can take any of the application and um, you can get to know that wherever your applications require some hardware based boards, you can use the FPGAs there. You can name them. You can think of like medical applications. There also you can use FPGAs. You can think of wireless applications. There also we can use FPGAs. You can think of IoT based applications. There also we can use FPGAs. Right. So these are all the categories where you will be able to use more oftenly on the FPGAs here. Excuse me. I'm sorry, a little bit cough is there for me. That's the reason. Okay, right. So let us see about the 7 series architecture, right? So when you take about the 7 series FPGAs, right? So almost all the FPGAs will have the logic resources. Okay, so they are called as slices. Okay, and they will be grouped in the configurable logic blocks. right? So this CLBs contains the combinational logic, okay, that is a lookup table, and they'll have each resources. FPGA will have their own register resources. That is called, we call it flip flop, okay, right? So they have some hardcore memories also available, like block RAM memories are there, right? And even the lookup table, whichever is available, they also can be used as memory here, okay? And there are some devices which are got hardcore multipliers also. For example, we have DSP48 slices, which can be used for multiplying 25 cross 18 bit numbers there. Means 25 bit and 18 bit numbers simultaneously, parallelly we can do a multiplication. That's the advantage for us, right? Right, and even the interconnect also, right? So interconnect is one thing which is very essential for us, okay, right? Because the from one lookup table to another lookup table, the interconnect may be readily available, or it should be made as programmable, right? So programmable means the correction will not be existing permanently. It is just for a time being purpose. Means until unless the program is running, that interconnect will be enabled for us. Once the power goes off, that interconnect will be erased. The FPGAs also will get erased. Okay, that's why we use some external memories to load the FPGAs from volatile to non-volatile memories. That's the reason behind that. Okay, right? Even we have some of the input and output buffers, which is our exact very important thing for interfaces from the FPGA and the outside world, right? So they are called the input output buffers. They have different standards will be there, right? So they supported. They are supported with the help of all the resources here. Okay, right? So apart from this, we'll be having the other resources like global clock buffers will be there, right? Boundary scan logic will be there, right? So all these things has to be taken care by the, right? Almost all the FPGA resources will have the same information, same things in our cases. Okay, right? So the alignment has been shown to you for your in your cases here. Okay, right? So right, so we have this red colors are there, right? So they are all the configurable logic blocks we call it as. Okay, right? So this green color indicates they are the block ramps. This one, they are the block ramps. Okay, and this one is a input output block, IO block we call it as. Right? So we have clock management tiles, this blue color, right? So they are called as clock management tiles because they are used in generating multiple clocks, right? So multiple clocks means I'll have only one input main clock there, and internally I want to have some sub other clocks, right? So this is called a, like in ASIC, if you see, it is called as clock tree synthesis. Means from one clock I'll derive other clocks. So they'll be using multiplier and divider to do that task, right? So the same here also we have some PLLs and MMCMs blocks are there. Okay, right? So they take care of generating multiple clock frequency, all this stuff required for us. I hope everybody is able to understand me. Any questions are there?
No, sir.
Okay.
One ma'am has raised the hand in chat box.
Okay, who is that?
Hindu, I think Hindu ma'am.
I think Indu madam has joined, raised it her hand long back only.
Okay, sir. Okay, sir.
It was initially only that she made it. Okay, no problem. Right. So this is the clock management tile we are having it. Okay, right. So in the we'll be having the FIFO logic, the first input, first output logic also will be there. Okay, right. So we'll be having a global clock buffer we call it as, right. So this is called means from here only the clock will be distributed to all the other resources. Okay, they'll be exactly on the center of the devices. Okay, right. So we have DSP48 slices. These two blocks is called multiplier and accumulator we call it as. Okay, so these two blocks are available here. Okay, and each of the inputs will have their own buffer. The 5O we got as in, right? So buff R is called as regional buffers. Okay, so what is this regional buffer is, right? So if I divide exactly, okay, I'll just show you this. Right. So if I take the FPGA into half section right this way, okay, and I will take one of this region, okay, and I'll take this as one more region, right? So this one is one clock region for us. This is in each of this region, they'll have some regional buffers for us. That's the reason. Okay, and they'll have the transceivers also, multi-gigabit transceivers, MGT we call it as. Okay, I hope everybody is able to understand me. Any questions are there means you can stop me at any point of time. Okay, right? Almost all the FPGAs will have the same resources. Okay, right? So now coming to our FPGA families. Okay, in 7 series, which is supported by Vivado. Okay, so now I would like to tell you very clearly that all these devices, whatever I'm informing to you, will be supported by Vivado only. Okay, right? So older versions of the Spartan 2, Spartan 3, and all is not supported by Vivado. Let me be very clear to you. Okay, right? So we have the 7 series FPGA families, right? We have Spartan 7, Arctic 7, Kintex 7, and Vertex 7. Okay, right? So based on your requirement and based on your specifications of the design, right, and how much resources are required, so based on that I can choose appropriately the devices here. Okay, right? So you might ask me a question like why there are multiple families, right? So most of the cases, some examples requires only a pure FPGA families. They don't require to have some transceivers and all those things, so they can go with Arctic Spartan 7, right? So in Arctic 7, right, it is also low cost family, but you'll have some small transceivers in this, right? So here we don't have any transceivers, right? So here we'll be having some of the transceivers, which can be like 6.6 gigabits per second will be there. Transceiver speed will be there for us. Okay, right? So Kintex, it's a mid-range device. Kintex is a mid-range device for us. Kintex is a mid-range device. This one, Kintex 7 we got it. This is a mid-range device. Okay, Vertex 7 will be always the highest performance. So, right? So we can't compare any of this performance with the Vertex 7. So when you are required to have some high performance is required, you can think of using the Vertex 7. Okay, right? Even the resource wise, you can see that it changes, right? So whatever I have depicted in this table for you, right? So logic cells like 102K, 215K, 478K, and 1965K, and all those things, right? So they are keeping it in mind that it's the largest device in that family. Okay, right? So we have range there. From it starts from 10K to 102K. Like that way, its ranges will be there for us, right? So in this case also, we are keeping it in mind the largest device in that particular family, and we are giving it to you the resources information to you. Okay, right? Even the block RAM there, right? DSP slices, how many are there? Even the transceivers, how many numbers are there? What is the speed it supports, right? So that's based on that, we will have the different families requirements here for us, right? I hope everybody is clear with that with this information. Any doubts are there to me? Right. So now let us see about what is Zinc. Okay, right? So Zinc is one family which is built with the same 7 series. Okay, I would like to inform you one more thing. The 7 series is whatever we are talking about, 7 series device, right? Spartan 7, Kintex 7, Vertex 7, and even now Zinc, right? So they are all manufactured with 28 nanometer devices. Okay, right? So in the ASIC technology, if it is ASIC means it's application specific integrated circuits. Okay, right? So when I want to manufacture an IC, integrated circuit component, right? So I need to go with some sort of technology cells, right? So some technology I should use, right? So this 7 series is built with 28 nanometer, right? So in Xilinx, we have moved across already. 7 series is built with 28 nanometer. We have ultra scale families, which is built with 20 nanometer. We have ultra scale plus families, which is built with 16 nanometer. And now we have come up with a very specialized device called as Versal. Versal ACAP we call it as, okay, right? So Versal is built with 7 nanometer FinFET devices, right? So we have moved across all the technologies, whatever is required for us, right? So Zinc is a complete SoC we call it as, right? Let us see about what is Zinc. Zinc is manufactured with 28 nanometer technology, okay, right? So it is what it is, right? Zinc, it's a combination of two things. One is programmable logic, means FPGA is there, as well as we have very special thing called as processing system. Okay, right? So in Zinc 7000, we have two numbers of Cortex-M processor. Okay, right? And we have some AXI interfaces which takes care of communicating from PS to PL. So these two are not two separate devices. This is a single device. Okay, this is a single device, right? So the processing system has got ARM processor. Okay, right? Programmable logic is similar to whatever we have discussed in the previous section, right? We'll have lookup tables, we'll have flip-flops, we'll have block RAM memories, DSP slicers. Some of them they have transceivers, some of them they don't have transceivers based on the device which you're targeting. Okay, right? So, right. So, what is the highlight of this Zinc 7000 family? Right? It is a complete ARM-based processing system. We got that, right? So we have an application processing unit. Okay, we have the application processor unit, which is having a dual ARM Cortex NN processor, which is a 32-bit processor. It is okay, right? We have cache and support blocks. We have fully integrated memory controllers. Means there are controllers, dedicated hard controllers available for interfacing with the memories, DDR2, DDR3, LPDDR, like that way. Okay, right? And we have IO peripherals also. Means it's a part of PS I'm talking about, right? So apart from this, we have this one. Tarun, I'm in one session. Can I call you later? Okay, right. Yeah, right. So we have IO peripherals also. Means if I want to interface some specialized peripherals, right? So we have some IO controllers available there. So we can use that also, right? So apart from this, we have a tightly integrated programmable logic also, right? So it means the PS and PL is having on a single chip. Okay, it is tightly integrated because it has got some AXI interfaces which can take care of communication from PS to PL. Okay, right? So what is the advantage of having this? What is the advantage? Any answers? Any answers are there? If I have processing system and programmable logic, so what is the advantage? Any answers from anybody? Anybody answers? Okay, right. So it's very simple, right? If I am in a manufacturing company, right? So what happens is for every components which I am putting on the PCB, right? So it includes some charges, right? That is called as charges are there. That area is in area will be included, right? So pricing will be different, okay, right? And area, the PCB area, right? And the tracks required for the routing and all those things. That area, that charges, that tracks laying those things, right? So all these things will comprise to me as it's called as bill of materials we got as, okay, right? So if I have a single device which can perform both the tasks, whatever the processor is doing and whatever a DSP processor is doing, right? If I am having it in a single chip, right, I'm saving that completely, right? So that's the advantage of going with this kind of devices. Am I clear? I hope everybody is able to understand me. Right, and very importantly, FPGAs are having a flexible arrays of inputs and outputs, right? Because it supports different standards, LV-CMOS, right? LVTTL, LVPECL, LVDS, JESDs, right? And even it supports uh, the SPI-based protocols, right? I2C based protocols, right? Different standards are supported for us. This is no problem for me, right? So apart from this, we have transceivers also, right? So and very importantly, I would like to tell you, right? So in the 7 series and above devices, right? So there are some analog to digital converter also available as a part of the programmable logic. Means I have an ADC built in inside my FPGA only, right? So I can give an analog input to that, okay, right? But it is sampling rate is just 1 mega samples per second, okay, right? So it has got 12-bit resolution is there, okay? We have two numbers or two channels of analog to digital converters in there in this case. Am I clear? Right? So this is the complete things. This is the chip whatever I'm talking to you about, the Zinc chip. Right? So we have Zinc 7000 series. Okay, right? So Zinc 7000, it has got, as I told you, it has got the processing system and programmable logic. You can see this. Okay, sorry. Right? We have processing system and we have yellow colored one, programmable logic here. Okay, right? So the processing system consists of dual ARM Cortex NN processor. Okay. So we have some of the device with even single core variant also. Okay, 32 kilobit of IND cache. This is L1 cache. 512 kilobit of L2 cache. 256 kilobit of on-chip RAM memory. Right. So the L2 cache is controlled by the Snoop control unit. Okay, right. We have timers. We have interrupt controllers. We have DMAs. Right. So each core is having its own neon or floating point unit engine we call it as. It's called coprocessor. Okay, right. So we have ARM core site multi-core trace and debug core also available on this. Means it is helpful for us to even debug the ARM processors. That's the reason behind that. Okay, right. So we have the AMBA switches running here across all these things. Right. AMBA means it is advanced microcontroller bus architecture we got as. Okay. As I told you, we have DDR controller, DDR3, DDR2, DDRP, DDR2. Okay, right. So static memory controllers, it supports quad SPI flash, NAND flash, NOR flash. Okay, right. And these are all the IO peripherals. Right. We have dual SPI controllers, dual I2C controllers, dual CAN, dual UART, GPIOs, SD card, USB, Ethernet. So all these things are there. Okay, right. So apart from this DMA, we have some peripherals along with their own internal DMA there. That's the reason, right? So we have some controller called as multiplexed input output, MIO configuration, we call it as multiplexed input output configuration, right? So this takes care of some of the IO pins to come out of this PS location, right? So generally this is having just 54 number of IO pins coming out here, okay, right? Right. So because of very less number of IO pins coming out of this PS system, right? So we have some of the peripherals coming out through this PL logic also. It's called as extended multiplexed input output, EMIO we call it as. Okay, right? So it is called extended multiplexed input output, right? This is multiplexed input output, MIO configuration and EMIO configuration. So this is configurable for me. Okay, what do you mean by configurable? Means I can select in the Vivado IP integrator, so which is my MIO configurator and which is my EMIO configurator. Okay, right? So apart from this, we have AXI interfaces. Okay, you can see here we have master AXI GP0 /1, slave AXI GP0 and 1. Okay, and we have slave AXI high performance ports HP0, HP1, HP2, and HP3. Okay, and we have slave AXI ACP port, accelerator coherency port here, right? So you can ask me what is the differences between this, right? So the general purpose, whatever we are having it, right? So those things, they'll be always 32-bit in nature, right? Whether you go with master AXI or slave AXI, they'll be 32-bit in nature, right? There are totally 4 numbers, 2 masters and 2 slaves, okay? And we have AXI high performance, which can be configured as 32-bit or 64-bit, okay? It's under our control, right? I can take it with the help of Vivado IP integrator here, okay, right? So we have one more port called as accelerator coherency port, okay? So what's the advantage of this is I can have a logic inside FPGA and that fellow can access directly the L2 cache of the processor. That's the advantage for us. That's why it's called as accelerator coherency port. Okay, is it clear? Right. So we have one more very important block. It's called as configuration block. Okay. Means always the processing system will come up first and then it will configure the FPGA. That's very important step here. Okay. Now you might ask me some questions like, okay, now how this fellow clocking will be there, other things will be there for me, right? So it is separate division. So the processing system has got their own clocking domain. The programmable logic has got their own clocking domain. Okay. You can individually work with only with processing system. You can individually work with only with programmable logic. That means I can write a VHDL or Verilog code, synthesize it, and I can deploy it on the FPGA. That's also is possible. Okay. I want to write some applications code with the help of on the processor to check it out whether my performance is my functionality is working fine or not in this case, right? I can write the application code using the VTIS and then I can check it out very properly, right? So they have their own clocks, internal, external clock capable pins are there. So from there, they will take the clocks for us, right? So internally, they have their own PLLs, ARM PLL, DDR PLL, IO PLLs are there. So they'll take care of distributing the clocks to all the other peripherals also. Okay, I hope everybody is able to understand. Any questions are there to me? Right. Okay. If you have any questions, please feel free to ask me. There is no issues. Right. So now, if I'm telling, like I want to have, this is a single chip we told, right? So this single chip, how we can have a clock synchronization, right? So we can, right? So I can have one clock given to from this to the processing system, okay, right? So we have an option here which takes care of generating the different clocks to the PL from the PS to PL communication, right? So they are called as PL fabric clocks, right? So those clocks will be derived from the PLLs, whatever is there here, okay, and that will be distributed to the FPGA. Means they can take care of synchronization also, right? But if you are giving externally, it's your responsibility to take care of synchronization and other stuffs, constraints and all. You should give it properly, okay? Right? There are 4 clocks coming from the PS to PL communication, so they take care of, right? And even they are also whenever we are generating the clocks, they are also in different frequencies. Also, we can generate. Like it can start with 0.1 megahertz to 250 megahertz. Like that, we can have a look on that, right? So this is about Zinc, right? So in a Zinc, we have seen only 2 processors. Now we can see that there is Zinc UltraScale Plus. This is built with 16 nanometer device. I told you, no, right? So this is called multiple SoCs, multiple processors here. Okay, you can see in this very clearly. We have Cortex A53 processor, Cortex R5 processor. We have ARM Mali 400 MP GPU, graphic processing unit. Okay, right? We have video codecs, right? All these are all blocks available for us. Right? So the Cortex A53, whatever you are having it right here, right? So they're all 4 in numbers. So it's called quad core, we call it as quad core, means 4 numbers of processor, and this is the 64-bit processor. Okay, and we have Cortex R5 processor, which is 32-bit processor. Okay, right? So we have an ARM Mali 400 MP graphics processing unit, which is having geometry processor and pixel processor. Okay, and they take care of the GPU sections here for us, right? So we have a security block which takes care of your encryption, decryption, right? Secure boot modding, and all those things will be taken care of by this block for us. Okay, we have a platform management unit which takes care of the power requirement to all of the processors, right? I can tell them very properly. Okay, we have DDR controllers which takes care of the DDR interfaces. It supports DDR4, DDR3, DDR3L, and LPDDR4 and LPDDR3 is supported. Okay, with ECC. ECC means error correction coding, error correction, and okay, right? Even with that one, right? We have on-chip RAM memory, which is 256 kilobyte, okay, right? We have 32 kilobyte of IND cache for Cortex A53, okay. R5 processors will not have the the L2 cache, okay, right? So we have 32 kilobit of IND cache. Instead of that, we'll have the ternary cam memory we got as TCM, tightly coupled memory we'll be having. TCM memory we got as. This is 128 kilobit. Okay, right? So in Ultra Scale Plus, apart from the block RAM and DSP slices, transceivers, and all those things, we have a specialized block called as Ultra RAM memories. Means I have some memories which is higher than block RAM sizes. That's the beauty of this one. Okay, is it clear? Right. So this is the evolution what we had it, right? So we came with only FPGAs, then we came with Zinc, then we came out with Zinc MPSoCs, right? So what are the goals, right? So how is it is useful for Python programming, right? So we'll be seeing about that a little bit later now, right? So we'll be using the Jupyter notebook and all other stuffs, okay, right? So what is the goal of this pink? It reduces the barrier. Whoever is working with the pink board, right? So they'll have limited experience in the hardware design, right? So they can use it very efficiently. That's the reason behind that. Okay, right? So it improves the productivity also. Like already who has worked with Zinc series architectures, right? So let us see about the Zinc, the Python framework here. Okay, the pink framework. Okay, right? So in the pink framework, we'll be having different sections here. Okay, as I told you, we'll be having an Vivado-based software is required to do an bitstream generation and other stuffs. Okay, right? Even with the Vitis, also there's no SDSOC now. It is called Vitis. Okay, right? So it is Vitis, right? So Vitis HLS and even with Vitis accelerators designs, I can use those applications, whatever is required for me to use it in the application in the PL section. So I can use it to accelerate the design very properly. That's why it is called as APIs. Okay, right? And most of them they require drivers. When you talk to any of the peripherals in the FPGA, right? So that requires some specialized drivers, right? So we use those drivers for that. Okay, right? So on top of that, we'll be having the Python APIs. Okay, like pink libraries will be there, right? So if I'm going with overlay for FPGAs, right? So they will be having PL overlays, GPIOs will be there, interrupts will be there, memory management input output will be there, right? So all these things will be there for me in this. Okay, right? So on top of that API, we'll be having the Jupyter or IPython applications there. Okay, and notebooks we call it as, right? So they are supported with different apps like Matplotlib, NumPy, scikit-learning, OpenCVs, and all those things are supported there in this. Okay, any doubts to me till now? I hope everybody is able to understand. Any questions are there? You can stop me if anybody has got some questions. Anybody is asking questions. Okay. Right. Right. So when you're talking about the drivers, right? So what happens is when you want to talk to any of the peripherals, right? So we need drivers. That is, what is a driver generally, right? It's a small, like it's a code written in C or C++ to take care of register movements, register data movement from one location to another location. That way it is called, right? So we use that kind of term as drivers for us, right? So Pink provides the next drivers for PS to PL interfaces, and it will be wrapped in the Python libraries, right? So they'll be already included in the Python libraries for us, right? So in the FPGAs, we'll be having the user design, the Pink overlays, and all those things will be built up, right? So there is built with the help of the bit streams, okay, right? So I can have different 5 types of drivers generally when I talk about in Zinc and programmable system, right? So I can have bit stream generated, okay. Now, if I want to download the bit stream, I need to use the JTAG cable, right? So, but with the Pink, what happens is, see, it is not for every complete new spec of bitstream generation. Okay, right? So Pink will provide already some predefined design will be there. In that, you have made some modifications, right? included some of the overlay designed by you only. Okay, right? So those things you want to download that bitstream to talk to the peripheral, right? So those kind of design bitstream loading is possible with the help of Pink. Okay, right? So that is done through the FPGA manager we call it as FPGA manager. Okay, through that we'll be able to download the bitstream, right? If I'm having any peripheral with GPIOs, right? So I have a system with GPIO drivers. Okay, if I'm having an interrupt, I'll be having the UIO drivers we call it as. Okay, right? So if I'm having some memory mapped IOs, I'll be using device memories. Okay, right? And specialized some Xilinx specialized device drivers are there. You can use those things also. Am I clear? Am I clear? Any doubts to me till now? Right? So you can get any of the design from the GitHub with a single Python command. Okay, you can just use this pip 3.6 install git plus https github.com/xilinx/pinkdl.git. Okay, you can go to that location. You can download any of the software style requirement for us, any of the packages required for us, right? So I want to download the bitstream. It's just a two-line command. Okay, right? It's just something like from Pink import the overlay. Okay, OL equals overlay and a bit file name we can name it, right? So in this case, when you want to do something, right? So always you should keep it in mind that we have the bitstream stored in the SD card. Am I clear? Am I clear? I hope everybody is able to understand me. Any doubts are there to be till now? Right? So when you have that completely, right? So we have a Jupyter notebook, right? So this is an open source generally. Okay, I think we got some questions. Let me just see. Okay, Hindu madam has raised a hand. Hindu ma'am, can you let me know? Okay. Right, so if you are not able to unmute, you can just ask your questions in the chat box. Later on, we can see that. Okay. Right. So we have Jupyter notebooks available, right? So this is an open source IDE. Okay, it opens in the browser only, so we can use those Jupyter notebooks for our Python interpreter here for us, right? So it's just like a plugin for a lot of IDEs required for us. That's the reason we use this Jupyter notebook IDE for us, right? So and we know very well there are some packages available for us for data analysis and visualizations, right? For example, NumPy, right? So we have a scientific computing package for Python. Okay, we have matplotlib, which is Python two-dimensional plotting libraries. Okay, and we have scikit-learning, which is for classification, regression, and clustering. Okay, and if you want to use OpenCV, it's majorly used for computer vision and machine learning softwares. Okay, right. So these are the optimized open source software libraries available for us for the Python for our Pink Z2 board. Any doubts are there? Right. So what are the Pink supported boards? We have Pink Z2 board, ZCU104 board, and ZCU111 board. Okay, right. So Pink Z2 will be from TUL. Okay, and Zinc MPSoC ZCU104 board will be from Xilinx. Okay, we have one more Pink board recently launched. It's called Pink ZU. Okay, right. So I can use applications anywhere. Right, wireless communication, wired communication, video systems and vision. Machine vision, medical systems, automotive systems, data center, machine learning algorithms, AI applications, military end applications, right? Everywhere you can use the complete tasks. I hope everybody is able to understand me. Any doubts are there to me till now?
No doubt, sir.
Okay, right. So let me start up the simple demo on this. Okay. I think there is some problem with presentation. Anything? Right. Is my screen visible?
Yes, sir. Visible, sir.
Right. So this is the pink Z2 board. Okay. Right. So this is they're having inside this. They have a Raspberry Pi connectors. It's not Raspberry Pi board. Is there? It's Raspberry Pi connectors are there. Okay. Right. We have Arduino connectors also. Right. We have headphone plus mic. We have line in. Okay. We have Ethernet connectivity. We have HDMI input and HDMI output. Okay. We have a cable JTAG or UART connector is there, which is a micro USB connector. Okay. Right. So through which I'll be able to connect the it for the UART also, and even I can download the bitstream also from that, and even that can be acted as power supply cable also, right? Or you can have external power input source also for us. Okay. There are two slide switches for user defined, buttons for system reset, four LEDs are buttons that's for user defined, and we have a RGB LEDs, red, green, blue LEDs we call it as. Okay, they're all user defined. Okay, remote ports also available for us for 3 hours. This is the USB host communication is there for us. We have SD card slot at the back of the board. Okay, and this is the Zinc 7000 FPGA in this. Okay, right. So this is how the connectivity will be done. Okay, we'll be using the USB powered. Okay, and I'll be inserting the SD card with all the required images. Okay, right. So I can download the pink image from the pink TUL board only. Means whichever the board you are using it, right? So they have their own Python pink based images are there. Okay, you can use those images readily available onto the SD card. Okay, this is the image will consist of what, right? It will consist of the Linux, the drivers, the bit files, the overlays, the Jupyter notebook, the Python interpreting the iping.ib files, right? So all these things will be there as a part of in the SD card only, right? So this is similar to like you have a single board computer, right? So instead of having an processor computer, I'll be using an external board here for us. That's what we'll do. Okay, right? So I'll be inserting that SD card inside the SD card slot. Okay, I'll be connecting the USB power USB cable to check it out whether it's booting properly or not. I'll have the Ethernet communication also, right? So Ethernet is required because if I want to download some packages, right? So I can use that Ethernet to share my internet from my host machine to target board, right? But we need to have separate interfaces also required, right? Is it clear? Any doubts to me till now? Any doubts are there? Any questions are there to me?
No, no, sir.
Okay. Okay. Right. So we will just demonstrate to you right now. Okay. So right. So let me just switch on my board. So I have connected the board very effectively. Okay. Right. I don't know whether I can turn on my camera or not because I have some problems in my camera. Okay, it's visual. Right, so I have connected this USB cable is there, right? So this is the USB port, okay? And we have the Ethernet cable connected here, right? So this too is connected to my laptop. That's what I'm trying to tell you. Is it clear?
Yes, sir.
Okay, right. Right, I have switched on the board, okay? I will just see whether how my Linux is booting there, okay? Right, so I'm using COM4. Okay, right. I'll just reboot it once for your interested. Right. So now it is booting. Can you see the booting sequence?
Yes, sir.
Right. So it is booting in the complete Linux here. Okay. So I have booted already, right? So it is coming as Xilinx at pink. It's coming for us, right? So if you want to see what is the IP address it has taken, you just type the command ifconfig, and you can see this is the IP address it has taken: 192.168.137.233. Okay, right? So what I can do is I can just go to my Chrome. Okay, you can type the IP address 192.168.137.233. Is what is my IP address, right? Yes or no? It's here 192.168.137.233. Right? So it will open up the Jupyter notebook for me. Right. So we got this extension. Okay. So this is the web page, like how it looks for when you start with your Python packages here. Okay. Right. So when you boot the images, right? So we'll be able to see what are the base, what are the logic tools, getting started, common, BNN, right? So BNN might not be available directly. Okay, we have to download some packages for that, right? So I've done that one already to save our time. Okay, right? So let me just start with getting started. Right. So if you want to see something like base overlay, let us see this. Right. So they're using some PMOD ADC and DAC example for this. Right. So I don't have that this one actually. Okay, the PMOD ADC and DAC connector. So I can just skip that one if it is interested or not. Right. You can see when you go to this running tab, I can see which are the terminals running the Jupyter processes. Right. So I can shut down if somebody is not like it's not using it very properly for us. Right. And doubts are there. This is the .ipynb. It's the overlay what we designed it for us. Okay, right? So this is how it will look like, right? So if you want to check it out very properly, right? So we'll be having like the notebooks, like we'll be having the you can have the new files uploaded. You can say you can upload it something. You can have a new terminal here. Like that way, I can start it with it. Okay, right? So even if you want to open this, create your own Python 3 terminals, right? So you can open that and you can make it your own way also. That's also is possible. That's also is possible, right? And we'll be having editor mode, like edit mode, right? So this is the command mode. That means it will be in the integrated in the gray border, right? But it will have a left margin will be of blue color here, whereas here it will be green color for edit mode. For command mode, it will be gray with blue margin, right? Even you can run, right? So we have some of the options here for us. I can run it, I can stop it, I can say markdown, like that way I can have it, right? You can use either the mouse or you can use the key navigations also. It's up to you how you would like to have it. Okay, right? So let me just take some simple example. Okay, I use a equals 30. I'll just run this, right? I want to print a. This is one example for us, right? So I want to use some kernel parameters. Like I want to import some time. Okay, right? I want to import some time. Okay, and then I want to say time sleep for some 10 seconds. Okay, you can see here it will import the time and it will wait for some time there. Right. So once it is done, this the indication of that timing, right? So that it will go for us, right? So I want to say hello from ping. You can run that command, okay, right? So I want to import some range I equals time. I want to import it, but I want to print from I equals range I 0 to 10 letters, take 10 it is, okay, and I want to run this, right? It will print one by one values, but it will have a sleep of 0.5 seconds, right? If I take, instead of 0.5, I can put it as 1.5 also, and I can run it again one more time if you want, right? The delay will be more. Is it clear? Any doubts to me till now? Right? You want to print the large outputs, you can print the large outputs within one short of time. We don't. We here. I didn't put any time limits for this. If I put time sleep, it will take some time to print all the outputs. Am I clear? Any doubts are there to me? You can generate the head, this one and all those stuffs. I hope everybody is able to understand. Any doubts are there? Let me know. Any doubts are there? Let me know. Okay, right. I'll move further then. Okay. Right. So I can have multiple outputs available. Like you can have, see, videos are there. I can have two options here. One is HDMI. I need to take one HDMI cable and connect it to this, right? And I can see the output on the HDMI output also. That's also is possible. It's up to you how you want to take it. Okay, right? Right. Even you can have the web cameras, OpenCV detection for HDMI or webcams, or even OpenCV filters are also implemented in this. That way also you can see them. It's also possible. Okay, right? So you can have some common things. Right? And if you want to have some logic tools to be included, Boolean generator, single stepping generator, waveform generator, you want to see that, you can see them. Just for your understanding purpose. See, here I'm importing some bit files, logictools.bit file. Then afterwards, based on my push button 0 and 3, right? So output will be on the LED2. Right? Whatever the logic I'm putting it in. Right? So I'll just do that. Right? You can see this mark, it is loading the bit files. Okay, right? I want to generate some this one. This is push button 0, this is push button 3, and this is the LED2. Okay, right? Right? Let me just run this. Right? I'm able to see the LED2 whenever I'm pressing any one of the buttons here, right? So either push button 0 or push button 3, the LED2 will glow because it's an XOR gate. XOR function I'm running. Am I clear? Right? Through Python I'm running it. Right? So I can change it. Even the entire Boolean function generation in single cell, whatever we had done it previously, right? So I'm doing that one. I'll stop it. Right. So I'm doing that function now. So whatever we did, right? So it is downloading the bit files, and you can see that output is coming properly or not. Right. So entire things, whatever we did, it can be in a single function. I can write it like this way also. That's also is fine. Am I clear? Any doubts to me? I hope everybody is able to understand. Any questions are there, means you please let me know. Okay. Right. Now let me just turn on this BNN application. This is a final demo which I'm planning to have, because I thought like I'll have some 10-15 minutes of question and answers kind of thing. That's the reason I just wanted to inform to you. Okay. Right. So anybody is not able to understand anything, please let me know. Right, so let me just bring out this CNV BNN CFR 10. Okay, right. So I'm importing the BNN packages here. So I'm using a command like import BNN. Okay, right. And we'll see what are the trained parameters available in that packages. Okay, right. Using a 1-bit for wait and activations, we are using it in this case. Okay, right. I can run it. I'll import the BNN first. So I'll be using this run command generally most of the cases. Right. So now let us see what are the available parameters. Right. So what are the available parameters on this network CNV W1 A1 means wait 1 and activation 1 bit. Okay. Right. I want to instantiate a classifier here for us. Right. So I have two classifiers. One is hardware classifier and another one is software classifier. Okay. Right. So in the hardware classifier, how much time it will take? In the software classifier, that is, I'm writing my own function in the Python coding to classify it. That's why I'm checking it. Is it clear? I hope everybody is able to understand me. Any doubts are there? Somebody has unmuted. Swapna, I think.
Sir, how did you write the function? And I mean, where you're calling from?
This is the class.
It is separate program for that
This is
PN
called.
classifier.
Yes.
Okay.
So this is we are using this CNV network topology there, no? So we are using a CNV classifier. Okay. Network parameters runtime. Okay.
Yes, sir.
Right. So now let me just the data sets of whatever we are having it. There are 10 classes of images in this. Okay. Right. So I will run that one. I'll print all those classifier classes. Right. I have aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. Right. So which image you want to clarify? You want to clarify? You want to open the airplane, or you want to open the deer? Just use deer.jpg. Okay. Right. How will I know which one is what? Right. So here pictures are there. Right. So here from here I am taking it. D-double-E-R it is. It's not small. It's not capital. It is small letter. Okay. I'll import that. Right. So we got this image. We got this image now. Right. So now I want to see the BNN in hardware. How much time it will take for to do it. Okay. Right. So the image will be passed on to the PL. Okay. And the inference is performed in this case. Right. So the Python API, whatever we are taking it, right? So they take care of the resizing of the images, format, and required for the network and all those things. They'll be taken care by the Python APIs there. Okay. Am I clear? I hope everybody is able to understand me. Right. So let me just see how much time it will take for us. Right. So I've taken, this is a hardware classifier. Okay. Right. I've taken the classify image as IM. IM is what you have given to this. Am I clear? Right. So I am taking this inference, whatever we take it, right? So it takes somewhere around 1583 microseconds. Okay, right? The classification rate is somewhere around 631.71 images per second, and class number is 4. And what class name it is? This deer. Okay. Now I want to check the same thing in the software classifier. Okay. So this is the Python uh, classifying class which what we are defined in the Python programming already, right? So I'll use the software classifiers in this. Means I'm running this on the software algorithm. Means on the processor side. Am I clear?
Sir, I think you have designed the hardware classifier with lot of images and software classifier with lot of images. From there, it is
Both are both are having same images, ma. No different images. I want to check it out now. I want to check it out the same image, whichever I have passed it right now. Whichever is passed, I am passing it right now, right? So how much time it is taking for software to classify it, and how much time it is taking it for hardware to get the classification. Okay, I'll run this output now, right? So you can see here it is almost like 1588661 microseconds, right? So in hardware it is very fast compared to software here for us. Am I clear?
But what is this hardware and software classification?
Hardware means in the FPGA. Software means in the system itself. If you write your own system in the computer itself, if you have having Linux, right? So when you write your Python coding, right? So how this classifier takes, how much time it will take for us to classification for the software, how much time it is taking it on the FPGA board. That's what I'm comparing this.
Okay, sir. Okay.
Okay. Right. Now let us see about the detailed classification information right now for us. Okay. Let me just see this. Right. So I want to display. Right. I'm importing one parameters called as display here. Okay. From the IPython.display classifier. Okay. There's a class. Okay. And I'm opening one images: car, airplane, bird. Right. I'm calling all these images. Okay. Right. So how much time it will take it for classifier for hardware? We'll see about those things. Right? I'll run it. Right? So car will take this much time. Aeroplane. Okay. How much time? Right? Bird. All these things. Right? So now I want to use some matplotlib libraries. Right? This is a Python library. Right? So we want to use that one. Visualize that one for us. Right? I want to build it. I want to plot those things. Am I clear?
So you want to prove that hardware is much better than software, sir?
Obviously, it will be faster, hardware. Am I clear?
Yes.
Okay. Right. So this is one plot library which we have used it in this. Right. Any doubts are there to me till now? Okay. So I can have different 1-bit waits and 1-bit activation, 1-bit waits and 2-bit activation. Like that way I can have it. Right. Let me just see. I'll import the BNN packages. I'll load the same deer.jpg image. Right. And I will see how much time it will take for 1-bit wait and 1-bit activation. W1A1 classification. Okay. Right. I'll use that. This is for hardware classification rate. How much time? This we already seen it. Okay. Right. You can have the image details completely. That's also is possible. Now let us change the weight. 1-bit weight and 2-bit activation. Okay. You can see now it is changed. 1629. Right. Even the rankings have been changed for us in this. Right. Right. Now we can have 2-bit weight and 2-bit activation also. Right. It is taken 4866 microseconds. So it is increasing when you have more classification given, right? So weights are more means it will take more time to check it out. Even in the software also it will be more high, very high. Right? Right? If you check the software, let us check the software for us. Right? So this much is for CNVW1A1 and this is for CNVW1A2 and next is for CNVW2A2. 2-bit weight and 2-bit activation. Right? I can plot those, all these libraries, hardware time, software time, and all those things. I want to plot this, I can plot it. Right? How much time it is taking in the hardware, how much time it is taking in the software, I can have it. And so you can even, this is for the weights, whatever we got it, okay? And now we can even think of putting it for rankings also. How much rankings are there? This is for W1A1, next is for W1A2, next is for W2A2. Right? Any doubts are there to be till now? Any doubts? Any doubts are there? Any questions, any doubts? Any doubts, please?
No doubts, yes, sir.
No doubts, right? Okay, that's fine. So I've kept this 10 minutes time for you to have questions and answers because should give you the time for them. That's the reason. Okay, right? So if there are no doubts, I have one small feedback form which is for our improvement purposes. Okay, right? So I want all of you to let me fill it out. Okay. Right, so there is one question from Sunil. Sir, hardware classifier, software classifier, these two functions are pre-built in libraries or you wrote it? See, they're all the Python classifiers. Okay, hardware libraries means it's something like C coding. Okay, in C code, when I want to transfer some email like uh, email data, something data to that, right? So we pass on that message, right? It's function written in the Python. That's what it is done. They're all the pink libraries. Right, so I have shared the feedback form in the link there. Okay, right, and if anybody is having some doubts, you can just let me know. They are all built in with the Python libraries, Pink libraries. You can. Any doubts are there apart from this? I have sent you one link for feedback form. You can just ask. You can just fill it out. Okay. Any doubts are there? You can just let me know. I'll be here. Okay. So, any other questions are there? That day you had asked for Rakshit.
Sir, I guess there are no questions from the participant side.
If
So,
yeah, okay, that's fine, madam. If you also are having anybody is having some doubts, you can just let me know.
yeah, okay, sir.
Because I just came to know from Rakshit and Banu. That's the reason I am just asking their questions.
No, no.
They should not be repeated their side because they'll not be able to answer those questions. That's the reason.
It's okay, sir. Thank you so much for your informative and wonderful session, sir.
Thank you, ma'am.
Thank you.
I hope everybody is able to understand me. If you have some doubts or something, you can contact me. I'll share my email address also in my chat box. Okay, it is prakash.g@coral.com, corel.com. Okay,
Okay.
you can contact me. Thank you.
Thank you, sir. Thank you.
Thank you, ma'am.
And I request all the participants to join for next session at 2 p.m. after the lunch. We'll providing the link in the group. Thank you so much.